Let's move into a different class of interactions, collisions. We'll define that as when objects start apart and then bump into each other. They collide. So continuing our saga on the frictionless ice, go ahead and read problem number 8. We're here, we introduce, dun dun dun, the physics bully, the villain of the story. On our physics field trip, there's always one in the group, right? He was forced to go along, he's a physics bully. He's upset about it, he doesn't want to go. There's no such thing as frictionless ice, he says. Of course there isn't, right? But, he's just upset for whatever reason. Okay, so unfortunately, this little kid gets distracted. He's going to run into the physics bully. They're going to collide. And here's the before picture. Why don't you just go ahead and sketch out what happens in the after situation. Notice it says the kid rebounds. What does that mean? Well, it means he's going in the opposite direction. So he comes in going to the left. That means he's going to rebound to the right. Looks rather upset there. I mean, he just hit the physics bully, of course. His bully. I don't know what's going on, right? But, all right. So they're going in opposite directions. The kid is M1, so he has V1 and V1 prime. This bully is M2, so he has V2 prime. We need to establish a positive direction. Here, I think it makes the most sense to call left positive because that's the initial direction of motion that the kid was moving in. Although if you want to just call right positive, that's fine. In the end, as long as you're consistent with your signs, you'll get an answer that agrees with my answer here as well. Let's start by writing out the law of conservation of momentum. Now, up to this point, there's been zero momentum in the system, but that's not the case anymore, right? The kid's coming in with a velocity. So why don't you go ahead and put all your numbers in and solve for the final velocity. Then we'll do the kinetic energy together. The physics bully is at rest, so M2V2 is going to be 0, but the kid has motion, right? And he's moving to the left, so he has a velocity of positive 3 meters per second. It says he rebounds, he's now going in the opposite direction, so his final velocity is going to be a negative 1 meter per second. And we're solving for V2 prime. Simple algebra, you should get positive 2 meters per second, and of course our sign agrees. We call left positive, we get a positive sign, everything's making sense. Now we go on to the next part here, we're going to calculate the total kinetic energy of the system before and after. Well, in the before situation, there's just the kid moving, so this is easy. We can call it KE1, and put subscripts on everything. That's 1/2 M1 V1 squared. Now just be careful. The equations for momentum and kinetic energy, they look an awful lot alike, so just pay extra careful attention, make sure you know where there's a half, where things are squared, where they're not. So go ahead and put your numbers in. I'm not going to show all the work here necessarily. It's real simple math. You should be getting 135 joules. And since physics bully is not moving, the total energy in the system beforehand is just the 135 joules. It's really just the sum of KE1 plus KE2, but KE2, the kinetic energy of the physics bully, is 0. So in this case, the total energy in the system beforehand is just 135 joules. What about in the after situation? Well, both objects are moving now, so we can calculate KE1 and KE2. 1/2 M1 V1 squared, 1/2 M2 V2 squared. Again, I'm not going to show all the work here, but you can show all the work on your page. Just to give you some checkpoints, you should be getting 15 joules for the kid and 120 joules for the physics bully. But they're going in opposite directions, so when we do KE total, should we be adding them or subtracting them because they're going in opposite directions, right? The kid takes his kinetic energy one direction, the physics bully takes his kinetic energy the other direction. Oh, but wait, kinetic energy is scalar, right? There is no directionality to it. As long as an object is moving, it has kinetic energy. So no matter what, I don't care what direction objects are moving, we will always be adding kinetic energies. So in this case, we're adding KE1 to KE2 for a total kinetic energy of 135 joules. Again, nice easy math. But something interesting has happened here. If you compare the total kinetic energy before and after, what do you notice? Hope you see, of course, they're the same. This is typifying a particular category of collisions. So back in our notes, we're going to be talking about the different types of collisions. There are going to be 3 different types. This first type is an elastic collision. This is when objects bounce off, they separate in some manner, and the total kinetic energy is conserved. It stays the same from beginning to end. It turns out there's actually a very unlikely situation to happen in the real world. It's kind of contrived. most collisions are not elastic. But in this one, all the math worked out, so the total energy before and total energy afterwards happen to match exactly. All right, let's go on to problem 9. Read it, sketch it out, assign a positive direction. Just go ahead and solve the whole thing. So now in the after situation, the little kid comes to rest. There he is, just scared out of his mind. Visibility again moves off to the left. I'm going to call left positive. You could call right positive, but literally everything is moving to the left, so I think calling left positive makes the most sense. We write out our law of conservation of momentum. The before situation is exactly the same as before, so there's no reason to even think it through. In the after situation, no, now the kid is not moving, so he has zero momentum. All momentum transfers over to the physics bully. And so his final velocity, magnitude and direction, should be positive 1.50 meters per second. I hope you all are still continuing to put the direction on your velocities. It does say magnitude and direction, right? If the instructions tell you to do so, you shouldn't be waiting for me to remind you about that. Put that positive sign on it. Again, we want to find the total kinetic energy in the system. In this case, there's only one object moving at a time, so it's real easy. In fact, in the before situation, you don't even have to recalculate it. I hope you didn't, because it's literally the same situation as problem 8, and so we already know it's going to be 135 joules. And now in the after situation, it's just physics fully moving. You do his kinetic energy, and you find it's 67.5 joules. So comparing beginning to end, was kinetic energy conserved? No, absolutely not. 135 to 67.5, there's no way kinetic energy was conserved. This is clearly not an elastic collision. This is an inelastic collision. Here, the objects bounce off again. They separate in some manner, but kinetic energy total is not conserved. So what became of the kinetic energy? We have another law, right? The law of conservation of energy, which says that the energy can't just be gained or lost. It's got to go somewhere. Well, just think about this. When objects collide, what sort of energy is produced? I hope you didn't say potential energy, because everything here was on the level surface of the ice. There was no change in height and there were no springs involved, so it's not potential energy. What does happen when objects collide? Oh, did I wake you up? Right. They hit and they make sound, and so some of the energy is released as sound energy. Also, when objects hit over and over and over, the molecules inside the objects, they vibrate more and more, and that is a transfer of heat. And so here, when we have a loss of kinetic energy, it transfers to some non-mechanical forms of energy, usually heat and sound. Let's do one more problem here, number 10. Go ahead and read it, sketch it out, positive direction, solve it to completion. Ooh, that physics bully, he's a nasty guy. He comes around, he's not going to take this, he's going to pick up the little kid. Now here, I'm not even going to draw the after situation, because I really do love to see what sort of pictures you draw. So I'm hoping next class you'll be able to show me your stick figures of what you think happens when the physics bully picks up the kid, how that looks. Now the physics bully is coming around, moving to the right, so I'm going to call right positive. If you want to call left positive, you can, but look, he's moving to the right, and we know together they move off to the right, so let's call right positive. And so we write out the law of conservation of momentum, but this time it's going to be a little bit different. They start apart, but then the physics bully picks up the little kid. So how can we show that they combine as one object, moving off with a common velocity? Well, the key is they combine as a single object. What combines is their mass. So here's how we change the law of conservation of momentum. We still write m1v1 plus m2v2. But in the after situation, we write out a combined mass, m1 plus m2. This case, we don't need v1 prime or v2 prime. They're going to move off as a single object. We can just call that v prime. Go ahead and put our numbers in. Remember, the little kid was at rest. He's just scared like a deer in headlights. He can't even move. But the physics bully, he swings around at the same speed he had from before, back at the end of problem 9, which was the 1.5 meters per second. We're calling right positive, so it's back to being a positive 1.5 meters per second. Here we combine their masses. You can just write it out like this, or add them together as 90 kilograms. And again, real simple math, which is one of the reasons why a lot of students really like momentum problems, because usually the math and algebra are very, very easy. And we should be getting a final combined velocity of positive 1.00 meters per second. Find the total kinetic energy in the system. Well, again, we don't need to reinvent the wheel. In problem 9, we already found the total energy of the system afterwards, right? Well, that means it's going to be the same as the before kinetic energy here, right? It's going to be the 67.5 joules. I hope you didn't recalculate, but if you did, that's okay. But, you want to try to make sure we're not reinventing the wheel. Now, in the after situation, it's definitely different. We should be getting 45.0 joules. So comparing before and after, was kinetic energy conserved? Not at all. But this is not an inelastic collision, because in an inelastic collision, you saw the objects separate. Well, that's not what's happening here. Here the objects are combining. This is our third category of collisions, a perfectly inelastic collision. It's as inelastic as they come. Here the objects combine, and once again, kinetic energy total is not conserved. The elasticity of some object is how well it springs back to its original shape when it's originally deformed. So when the objects collide, they sort of deform in some way, and if they can spring back to their original shape with no loss of energy, we say that's very elastic. But like I said, that's a very contrived situation. In the real world, it's very rare to have an actual elastic collision. Most collisions are inelastic to some degree with a loss of energy. And then again, if the objects combine and move off as a single object, that is our perfectly inelastic collision.